Bayesian decision theory classification. We discussed the credit scoring in section 1.2.2 where we saw that in a bank, according to their past transactions, some customers are low risk in that they paid back their loans and the bank profited from them, and other customers are high risk in that they defaulted. Analyzing this data, we would like to learn the class high-risk customer so that in the future, when there is a new application for a loan, we can check whether that person obeys the class description or not and thus accept or reject the application. Using our knowledge of the application, let us say that we decided that there are two pieces of information that are observable. We observe them because we have reason to believe that they give us an idea about the credibility of customer. Let us say, for example, we observe customers' yearly income and savings, which we represent by two random variables, x1 and x2. It may again be claimed that if we had access to other places of knowledge such as the state of economy in full detail and full knowledge about the customer, his or her intention, moral codes, and so forth, whether someone is a low-risk or high-risk customer, could have been deterministically calculated. But these are non-observables, and with what we can observe, the credibility of a customer is denoted by a Bernoulli random variable C conditioned on the observables x, which is equals to x1, x2 to the transpose, where C is equals to 1 indicates a high-risk customer, and C is equals to 0 indicates a low-risk customer. Thus, if we know the probability of C conditioning on x1, x2, when a new application arrives with x1 equals to little x1 and x2 equals to little x2, we can choose the following. We can choose that C equals to 1 if the probability of C equals to 1 conditioning on little x1, little x2 is greater than half, and we choose C equals to 0 otherwise, or equivalently. If we might choose that C equals to 1 if the probability of C equals to 1 conditioning on x1, x2, which is greater than the probability of C equals to 0 conditioning on x1, x2, and C is equals to 0 otherwise. I mean, these are just two different forms for representing the same meaning. And the probability of error is 1 minus the maxima chosen among the following two probabilities. The first one is the probability of C equals to 1 conditioning on x1 and x2. The second is the probability of C equals to 0 conditioning on x1 and x2. This example is similar to the coin tossing example except that here the Bernoulli random variable C is conditioned on two other observable variables. Let us denote by x the vector of observed variables, x equals to x1, x2 to the transpose. The problem then is to be able to calculate the probability of C conditioning on x. Using Bayes' rule, it can be written as P of C conditioning on x is equals to P of C times P of x conditioning on C divided by P of x. So P, the probability of C equals to 1, is called a prior probability that C takes the value 1, which in our example corresponds to the probability that the customer is high risk regardless of the x value. It is called the prior probability because it is the knowledge we have as to the value of C before looking at the observables x, satisfying the probability of C equals to 0 plus the probability of C equals to 1, which is equals to 1. The probability of x conditioning on C is called the class likelihood and is the conditional probability that an event belonging to C has the associated observation value x. In our case, the probability of x1, x2 conditioning on x equals to 1 is the probability that a high-risk customer has his or her x1, which is equals to little x1, and x2, which is equals to little x2. It is what the data tells us regarding the class. P of x, the evidence, is the marginal probability that an observation x is seen, regardless of whether it is a positive or negative examples. That is, the evidence P of x is equal to the summations of P of xc, summing for all possible c, and which is equals to the following combinations of two conditional probability. That is, the probability of x conditioning on c equals to 1 times the probability of c equals to 1 plus the probability of x conditioning on c equals to 0 times the probability of c equals to 0. So combining the prior and what the data tells us using Bayes' rule, we calculated the posterior probability of the concept, P of c conditioning on x after having seen the observation x. Posterior is equals to prior times likelihood divided by evidence. Because of normalization by the evidence, the posteriors sum up to 1. That is, the probability of c equals to 0 conditioning on x plus the probability of c equals to 1 conditioning on x is equals to 1. Once we have the posteriors, we decided by using equation 3.1. For now, we assume that we know the prior and likelihoods. In later chapters, we'll discuss how to estimate P of c and P of x conditioning on c from a given training sample. In the general case, we have k mutually exclusive and exhaustive classes, Ci, where I is index starting from 1 to 300 k, and for example, in optical digit recognition, the input is a bitmap image and there are 10 classes. We have the prior probability satisfying that the probability of Ci, which is greater than or equals to 0, and the summations of probability of Ci, summing for index I starting from 1 to k, is equals to 1. The probability of x conditioning on Ci is the probability of seeing x as the input when it is known to belong to class Ci. The posterior probability of class Ci can be calculated as the probability of Ci conditioning on x is equals to the probability of x conditioning on Ci times the probability of conditioning the probability of Ci divided by the probability of x, which is equals to the probability of x conditioning on Ci times the probability of Ci divided by the summations of the probability of x conditioning on Ck times the probability of Ck, summing for all index k starting from 1 to capital K, the number of classes. And for minimal error, the Bayes classifier chooses the class with the highest posterior probability. That is, we choose Ci if the probability of Ci conditional on x is equals to the maxima, chosen among all the probability of Ck conditional on x, where k is where the maxima is taken among all possible k.